In this problem, we'll be dealing with a geometric sequence, the terms of that sequence, and also with an infinite series, which will be the sum of those terms. Now, a geometric sequence is simply one in which each term after the first is multiplied by the same number to get the next term. And the number you multiply by is called the common ratio. Now, if you add those terms, then you're talking about a series. You could have an infinite or a finite series. So let's look at this first problem that has 4 parts. We have a bouncing ball. A ball is dropped from a height of 30 feet. Each time it strikes the ground, it bounces up 0.8 of the previous height. So it drops 30, and then it goes back up 0.8 or 80% of that distance, which is 24 feet. And then it falls again, and then it goes up again 0.8 of that distance. And it continues until the ball comes to rest. It doesn't bounce anymore. So let me go down to look at first. The sum of the first 10 terms of a geometric sequence is given by, so this is the format, sum of n terms, a1 say is the first term, then it's multiplied by r to get the next one, and multiplied by r again to get the next one, and so on. And then they give you this formula to find the sum of n of those terms. So for example, let's say I have a sequence. The first term is 4. I multiply that by 1/2. I get 2. Multiply by 1/2, so r is equal to 1/2. That's the common ratio. This will give me 1. And then I multiply again by 1/2. That gives me 1/2. Multiply by 1/2 again, I get 1/4. And then you could stop at any point and just add up those terms. So we had the 4, the 6, and the 1. Get 7, and then 1/2, and then add the 1/4 to that. And that would give me the sum of those 5 terms. But it's possible that we have one that goes on forever. Infinite. And we want to know the sum of that series. Then it becomes a series. Well, there's the formula. Convergence of an infinite geometric series. So what if we have the terms of a sequence and we want it's infinite? K equal 1 to infinity. This tells me that if the common ratio is less than 1, or the absolute value is less than 1, which means it has to fall between -1 and 1. If it's 1 or greater, it's not going to work. Or if it's -1 or less than that, it's not going to work. It has to be between -1 and 1. It turns out that the sum of that infinite series is given by this formula. So let's look at the one I had. I had 4, and then 2, then 1, then 1/2, and then it keeps on going forever. Does this converge? Well, according to this theorem here, if the common ratio is between -1 and 1, it will. And this one does, because you're multiplying by 1/2. 1/2 is less than 1 and greater than -1. So according to this, the sum will be given, and you can kind of approximate this. You have 4, 2, 1, that's 7 1/2. And then we add 1/4 to that, and you can see what it's approaching. According to this, you take the first term, divided by 1 minus the common ratio. The common ratio is 1/2 here. So that gives me 4 divided by 1/2. So if I were to add 1,000 of these, the terms of this sequence here, to get the series, it's going to get close, but never go over 4 divided by 1/2 is 8. And you can kind of see what's happening. Got 4, 2, 1, that's 7, and then you have 1/2, and then you're adding a fraction to that, another fraction to that. So the fractional part keeps getting closer and closer to 1. Eventually it approaches 1. You have 7 and 1 gives me 8. Okay, so that's the idea of convergence. sequences. Well, if you have one like this, you have 4, and then it's 8, and then it's 16, and then it's 32, and so on. Here the common ratio is 2. I'm multiplying by 2 every time. So you can see this is going to get larger and larger and larger. It's not going to converge. And of course 2 is not in the interval between -1 and 1. Okay, so we're going to use some of these ideas, this problem here. So the ball drops from a height of 30 feet. Each time it strikes the ground, it bounces up 0.8 at the previous height. Let me space these out a little bit. What height will the ball bounce up to after it strikes the ground for the 3rd time? So 30 feet from a height of 30 feet. And then it bounces up 0.8 or 80% of the 30. So we multiply that by 0.8. So that would be for the first bounce. For the 3rd bounce, you can see it's just going to be multiplying this by 0.8 again, then 0.8 for the 3rd one. So we get this. So we use the calculator. Okay, 30 parentheses 0.8 to the 3rd power. Get 15.36. So the answer to part A, 15.36. And this is in feet. So this one's pretty straightforward. How high will it bounce after it strikes the ground for the nth time? Well, pretty much the same thing as part A. 30 is always multiplied by 0.8. The bounce was 3, so for the nth, this will just be n. So it bounce for the formula, if you want, is 30 times 0.8 to the nth. This one, how many times does the ball need to strike the ground before its bounce is less than 6 inches? Okay, bounce has to be less than 6 inches. So let's set it up this way. So it's going to be 30 multiplied by 0.8 to the nth. And we're going to set this equal to, now this 30 is in feet. So we want the 6 inches in feet also. So I'm just going to put 0.5 here. That'll be 0.5 feet. Now we can solve this for n, and that would tell me how many bounces, so that the distance of the bounce would be 6 inches or half a foot. And if I want to go less than that, I simply just increase it by a little bit more, as we'll see here. So what I'm going to do is 0.8. I'm going to solve this for n. Divided by 30. Now I'm going to take the natural log of both sides. Now I could use base 10, it doesn't really matter here, but I shall use natural log. So I have a ln of 0.8 to the nth is equal to ln of 0.5 over 30. And this, of course, is this whole thing here. Properties of logs. Properties of logs allow me to take this exponent here and bring it over here as a coefficient. So this would be n. Natural log 0.8 And that's going to equal to this part right there. Divide both sides by the natural log of 0.8 to solve for n. So this will be ln 0.5. Remember that 0.5 is in feet over 30. And this will be divided by natural log. I'll take the calculator then, and I'm going to compute the expression on the right side. So it's ln of 0.5 divided by 30, and close the parentheses, and then I'm going to divide that by ln of 0.8. So that means that it has to bounce 18.348 times, so that the length or distance of the bounce is 6 inches or half a foot. Now we want it to be less than 6 inches. So that means we have to go one more bounce. So the answer to this one is 19. How many times does the ball need to strike the ground before its bounce is less than 6 inches? So at 18 plus bounces, it's going to be equal to 6. So if we go one more bounce, that should make it less than half a foot or 6 inches. So the answer to this one is 19. 19 bounces. So these I think are pretty straightforward. Number 19, or number part D I should say, it's a little bit more interesting. What total distance does the ball travel before it stops bouncing? What total distance does the ball travel before it stops bouncing? So here's what happens. The ball falls from a distance of 30 feet. Okay, so that travels that distance. So we're going to set this up as a sequence, geometric sequence. And then it bounces up 0.8 of that. So I'm not going to multiply it, I'm just going to leave it in this format. 0.8. Okay, so it goes down 30 feet, and then it goes up 30 times 0.8 of that, or 24 feet. But then remember, it falls that same distance back again. So I have to put this one twice. Okay, so falls 30, goes up 30.8, and then it falls down that same distance, 30.8. And then it goes up 0.8 of that previous distance. So I'll just put a square on this one. And then it falls that same distance. And then it goes up 0.8 of the previous distance, which again, we just multiplied by 0.8, so that'll be a 0.8 to the third. But then it falls that same distance. And it would be 30.8 to the third. Now I'm going to break this down into two series here. The first one, I'm going to take the 30. So say, okay, 30 plus 30 times 0.8 plus 30, 0.8 to the second, and we're going to call this an infinite series. even though the ball does stop bouncing. And then what do I have left for the second series? Well, I have two of these. Okay, I already used one of them, 30 times 0.8 for the first one. I have one left over, so I'm going to start here, 30. Then remember, I had two of these 0.8 squared, so I'll take another one and put it here, so 30. And the same thing with the 0.8 to the third. I could put one over here and one over here. So if you look at these individually, each one of these represents a series, and they're infinite. So if I look at this for the first series, the first term is 30, and you can see I'm multiplying by 0.8 every time. So according to the formula I showed you, we're treating this like an infinite. It's like the ball just continues bouncing a bunch of times and then eventually comes to rest. But we can still treat it as a series to get pretty close to what the answer is supposed to be. A1 is the first term of that first series, so that'll be 30 over 1 minus 0.8. So this will be 30. 1 minus 0.8 is 0.2. So this is equal to 150. Now for the second one, again, pretty much the same sort of thing, except the first term now for that one is 30.8, and I'm still multiplying by 0.8. Say the first term is 30 times 0.8, and I'm multiplying each term by 0.8, so the sum, using the formula we looked at, is equal to the first term, which is 30, times 0.8. The denominator is still going to be the same, because it has the same common ratio of 0.8, so 1 minus 0.8 is 0.2. So we add those up. The total distance that the ball travels before it comes to rest is 270 feet. Thanks for watching. We'll see you next time.